Hello everyone, welcome to my channel. You must have heard about natural numbers, whole numbers, integers and rational numbers in your previous classes. In this lecture, I am going to introduce you with two more types of numbers, real numbers and irrational numbers. And if we start from real numbers, my number system will look like this. So real numbers include rational numbers and irrational numbers. We know the rational numbers are the numbers which we can write in this form P upon Q, where P and Q are integers and Q is not equal to 0. And these rational numbers include integers. Integers include negative natural numbers and whole numbers include natural number and 0. In this lecture, before discussing about rational numbers and irrational numbers, we will discuss about real numbers and their decimal expansion. After that, we will discuss rational numbers, irrational numbers on number line, representing real numbers on number line, decimal form, operation on real numbers, and last, laws of exponents for real numbers. At the end of this video, we will also discuss about the surds or radicals. So do watch this video till end. Now let's discuss about decimal expansions of real numbers, and we will see how we can use these decimal expansions to distinguish between rational numbers and irrational numbers. Okay, we have three types of decimal expansion. First is terminating, second one is non-terminating recurring, and third one is non-terminating non-recurring. Let's see what is terminating decimal expansion. For this, I will take one number, real number 1 divided by 8. Now let's divide 1 with 8. So I will get my answer like 0.125. I can write here 0.125. See, my remainder here is equal to 0. So we can say that this division is exact or remainder is equal to 0. And such decimal expansions are known as terminating, and the quotient of such divisions are called terminating decimals. Means 0.125 is a terminating decimal. So next type of decimal expansions, we have non-terminating recurring. To explain this non-terminating recurring decimal expansions, I will take 2-3 examples. Let's divide 1 with 3. What will we get? If I divide 1 with 3, I will get my answer like 0.3333, and it will go on. It will never end. Then I'll take one more example. If I divide 11 with 30, so my answer will be like 0.3666, and it will go on. And let me take one more example, 4 divided by 7. So here my answer will be like 0.571428. Then again 571428, and it will go on. It will never end. So here see, in first example, this 1 divided by 3. So here this 3 is repeating again and again. And in second example, 6 is repeating again and again. And in third example, this 571428, this set of digits, they are repeating again and again. So it means that the process of division will never end. Means it will not terminate, and we will not get remainder equal to 0. Such decimal expansion in which a digit or a set of digits repeats continuously are known as non-terminating recurring, and the quotient of such non-terminating recurring decimal expansions are known as non-terminating recurring decimals. So here 0.333, 0.3666 and 0.571428 are non-terminating recurring decimals, and we can represent these as simply by putting a bar on repeating digit. Like 0.3, I can write this as 0.3 bar, means 3 is repeating again and again. Similarly here 0.36 bar, this digit 6 is repeating. So this I can write 0.571428 and bar, means this set of digits are repeating again and again here. And always remember that these terminating decimals and non-terminating recurring decimals are rational numbers. And in next topic of rational numbers, we'll prove that how these terminating decimals and non-terminating recurring decimals are rational numbers, means that we can write them in P upon Q form. Now the third and last decimal expansion, non-terminating, non-recurring. Non-recurring means we do not have any digit or set of digits which are repeating again and again. So for this also I will take few example. So first example here, if I take 3 divided by 7, so my answer will be like 0.42857142 and it will go on. Means here also we won't get any remainder equal to 0. Similarly, if I divide 18 with 23, so my answer will be like 0.782686 and it will go on. So here also the division will never end and we won't get any remainder equal to 0. Such decimal expansions are known as non-terminating, non-recurring, because here we do not have any repeating digit or set of digits. And the quotient of such divisions are called non-terminating, non-recurring decimals. So 0.42857142 so on and 0.782686 so on are non-terminating, non-recurring decimals. These non-terminating, non-recurring decimals are irrational numbers and we cannot write them in P upon Q form. Now let's discuss about rational numbers. Rational numbers are the numbers which we can write in P upon Q form where Q is not equal to 0. All whole numbers, natural numbers and integers are rational numbers. All fractions are rational numbers, and in previous topic we have learned that terminating decimals and non-terminating recurring decimals are also rational numbers. With the help of few examples, I will prove that how the terminating decimals and non-terminating recurring decimals are rational numbers. So let's get started. For that I will take 2-3 examples. First example here I have taken, show that this decimal number 3.142678 is a rational number. See, this number is a terminating decimal. So we know what are the rational numbers which we can write in the form of P and Q where Q is not equal to 0. So see here, this 3.142678, I can write this number as 3142678 divided by 6 zeros, correct? So it means I have written this number in P upon Q form, and here Q is equal to this number, and see, and this is not equal to 0. It means I have represented this number 3.14278 in P upon Q form. So this number is a rational number. So let's take one more example of. So in this example we have to show that 0.3333 is a rational number. We know we can write this number as 0.3 bar. So now let's take let's take x is equal to 0.3333 and so on. Now multiplying both side by 10, this will become 10x is equal to 10 into 0.3333. If I multiply this number, I will get this is equal to 3.333 and this 3 will go on, and we know that this is equal to x. So here we can write this as 3 plus I'm splitting this number in two parts. So I can write this as 3 plus 333 and so on, and this is equal to my x. So here I'll put this value. This will become 3 plus x. So now I will solve this equation for x. So this will become 10x minus x. I will take this x to other side is equal to 3. So I will left with 9x is equal to 3. So here x is equal to 3 by 9, which is equal to 1 by 3. It means I have represented my x 0.333 in 1 by 3, means P upon Q form. So it means this number 0.333 is a rational number. This is P upon Q form, and here Q is equal to 3, which is not equal to 0. So it means x is equal to 0.3333 is a rational number. So now let's take one more example where set of digits are repeating themselves. So similarly, show that 1.272727 and so on, which we can write like 1.27 bar is a rational number, means that we can write this number in P upon Q form where Q is not equal to 0. So similarly here I will take let x is equal to 1.272727 and so on. Here how many digits are repeating themselves? 2 digits are repeating. So I will multiply this x with 100. So this is 100, x is equal to 100 multiplied by 1.272727. So this will become equal to 727 and so on. So see here I can split this number like 127 plus 0.272727 and so on. See this here so here this is 0.272727 but I want this number to be equivalent to x. So for that I will split this 127 like this. See, I can write this 127 as 126 plus 1 plus 0.272727, and now I will combine these two numbers. So this will become 126 plus 1.272727. So see, this 1.272727 is equal to x. So here I can write this. So it means 100x is equal to 126 plus x. So so now I will solve this equation for x. So this will become 100x minus x, which is equal to 126. So this will become 99x divided by 126. So x is equal to 126 divided by 9, and this x is equal to, I have taken 1.2772727 and so on, equal to 126 divided by 99. So I have represented this number in P upon Q form where Q is equal to 99 and this Q is not equal to 0. It means this is a rational number. And we'll do more such questions in exercise 1.3 of NCERT book. Prove that the terminating decimals and non-terminating recurring decimals are rational numbers. Sometime in your exam you'll get questions like, without doing any division, find whether the given rational number is terminating or non-terminating. prove that the given rational number should satisfy these two conditions. First condition is that the rational number should be in P upon Q form, where Q is not equal to 0 and P and Q are integers with no common factors other than 1. And second condition here is to write our denominator in the form 2 raised to power m into 5 raised to power n, where m and n are whole numbers. If the given number is satisfying these two conditions, then we can say we can convert this rational number into a terminating decimal. To make this concept more clear, let's do this exercise here without doing actual division. Okay, we have to show that which of these rational numbers have terminating decimal representation. So first we'll check with first question. So first here we have 17 divided by 50. So this, see, the P here is 17 and Q here is 50, correct, and Q is not equal to 0 and 17 and 50 have only one common factor, that is 1. So it means first condition is satisfied, and second condition we have to check whether denominator, here denominator means Q is equal to 50. So here we'll find the factors of 50 like this. So we can write this 50 as 2 into 5 into 5, means 2 raised to power n multiply by 5 raised to power 2. So it means we are able to write this 50 in the form of 2 raised to power m into 5 raised to power n, and here m is equal to 1 and n is equal to 2. It means this number 17 divided by 50 is a terminating decimal. Okay, so it means we can write this as a terminating decimal, is a terminating decimal. 8. Second number we have 7 divided by 8. So here see, P is 7 and Q is equal to 8 and their common factor is 1. So first condition is satisfied, and second condition we have to check whether we are able to write this Q means 8 as 2 raised to power m into 5 raised to power n. So let's see, we know the factors of 8 are 2 into 2 into 2. So we can write this as 2 raised to power 3 multiply by 5 raised to power 0. So it means we are able to write this as 2 raised to power m into 5 raised to power n. So this is also a terminating decimal. So this is a terminating decimal. So last question here we have 23 divided by 72. So we can write this as, here P is 23 and Q is equal to 72. Their common factor is only 1. So first condition is satisfied. Second condition we have to find the factors of 72. We know the factors of 72. We can write this 72 as 2 into 2 into 2 into 3 into 3, means this 2 raised to power 3 into 3 raised to power 2. Correct, we are not able to write this as 2 raised to power m into 5 raised to power n. So it means 23 divided by 72 is not a terminating decimal. Okay, so now we can find the given rational number is terminating or not terminating. Always remember that there are infinite rational numbers between two given rational numbers. And now we'll see how we can insert rational numbers between two given rational numbers. So there are three methods of doing this. Method says if a and b are two rational numbers, then their mean a plus b divided by 2 is also a rational number and its value always lies between a and b. So here we have two conditions. First is if a is less than b, then a will be less than a plus b divided by 2, and this a plus b divided by 2 is less than b. And second condition here we have if a is greater than b, then a will be greater than a plus b divided by 2 and a plus b divided by 2 will be greater than b. So let's take one example and see how we can use this method to insert a rational number between two numbers. So here I have taken this example. Insert two rational numbers between 7 and 8. Rational numbers are 7 and 8. 7 and 8, and the mean of these two numbers will be 7 plus 8 divided by 2, which is equal to 15 divided by 2. So this number 15 divided by 2 will be between 7 and 8. So I can write this as 7, 15 by 2, 8. So here I have inserted one number between 7 and 8, that is 15 divided by 2. Now to find the second number, so what will I do? I will find the mean of either 15 divided by 2 and 7 or 15 divided by 2 and 8. This means 7 plus 15 divided by 2, which is equal to 14, 15. So this will 29 divided by 2. So this is between 7 and 15 divided by 2. So I will get 7, 29 by 2 and then 15 divided by 2 and 8. So two numbers between 7 and 8 are 29 divided by 2, 15 divided by 2. And one other option here we have, if we take second number between 15 divided by 2 and 8. So that will be 15 divided by 2 plus 8, which is equal to 15 plus 16 divided by this will be equal to 31 divided by 2. So my numbers will be in this case 7, 15 divided by 2, then 31 divided by 2 and 8. So here I have two answers. One is this and another one is this. We use this method to insert rational numbers between two integers like 7 and 8 I have taken here. And second method, for any two integers like fractions we have a divided by b and c divided by d. A plus c and b plus d is also a rational number, and this a plus c divided by b plus d lies between a divided by b and c divided by d. So let's take one example over here. Find three rational numbers between 3 by 5 and 4 by 7. So here we will use this method. So for that my given numbers are 3 by 5 and 4 by 7, and this number will become 3 plus 4 divided by 5 plus 7, which is equal to 7 divided by 12. So this number always lies between 3 by 5 and 4 by 7. This is my first number. So I can write this as 3 divided by 5, 7 by 12 and 4 by 7. So next we have to find two more rational numbers. For that what can I do? I'll join their numerator and denominator like this. So I will get 3 plus 7 divided by 5 plus 12, which is equal to 10 divided by 17. So this number will be between 3 by 5 and 7 by 12. So I can write this as 3 by 5, 10 by 17, 7 by 12 and 4 by 7. So one more number I have to find, because I have to find three rational numbers. For that you can take this combination, you can take this combination, you can take this combination. It's your wish only. So I will take this combination, this one, 3 by 5, 3 plus 10 and 5 plus 17. So this will become equal to 13 divided by 22. So this will be 3 by 5 divided by 13 divided by 22, and then 10 divided by 17, 7 divided by 12, and 4 divided by 7. So this is my answer. So from here we can see that there are infinite rational numbers between two rational numbers, and we can find them with next method. Third method here we have, and we used it. Third method here we use to insert more rational number, means more than 3. For example, third method, and this method we use to insert more rational numbers between two rational numbers. Suppose we have to insert 5 rational numbers, 6 rational numbers, 7 rational number, then we will use this method. So for that I will take one example. So this example says insert 7 rational numbers between 5 divided by 6 and 7 divided by 9. So first we will make these two rational numbers like fraction. So for that I will take, first step here I have to take LCM of denominator, means 6 and 9, which is equal to 18. Correct? And second step here which I have to take, I will make them like fraction, like 5 by 6 multiply by 3 by 3, which is equal to 15 divided by 18, and this 7 by 9 multiply by 2 divided by 2, which is equal to 14 divided by 18. So the denominators of both numbers are same now. And third step here is, so here how many numbers we have to insert? We have to insert 7 numbers. So we will multiply both the numerator and denominator of both the rational numbers by 7 plus 1, means 8. So here 15 divided by 8, we have to multiply with 8 both the numerator and denominator. After multiplying this we will get 120 and 144. And for second number 7 by 9, we have to multiply with 8 divided by 8, which is equal to, next we have to multiply this 14 divided by 18 with 8. So we will get 112 and 144. So here see the denominators are same. So we can write 7 rational numbers between these numbers, and these will be, count 120 divided by 144. After 120 what will come? 121 divided by 144, then 122 divided by 144, then 123 divided by 144, then, so here see 1, how many numbers we have to write? 7. 1, 2, 3, 4, 5, 6 and 7. So my last number will be 112, 144. So here see we have 120 and here we have 12. So we'll write number like 119 divided by 144, 118 divided by 144, 117 divided by 144, 116 divided by 144, 115 divided by 144, 114 divided by 144, 113 divided by 144. So these are my numbers, 7 numbers which we can insert between these two rational number, and these two rational number are 5 by 6 and this is 7 by 9. And if you want to simplify these numbers, you can simplify these number also. So first number will be remain same, 119 divided by 44. Second will become 59 divided by 72, and third will become 13 divided by 16. Next will become 29 divided by 36. Next will become this will remain same, 115 divided by 144 and 19 divided by 24, and last will be same. So and we'll do this type of question in exercise 1.1 of NCERT book class 9. So next we have representation of rational numbers on number line. In previous classes we have learned that we can represent all rational numbers, means natural numbers, whole numbers, integers and fractions on number line. So here we are not going to discuss about this more, and later in this video we will discuss how we can represent terminating decimal and non-terminating recurring decimals on number line. Now let's discuss about irrational numbers. Irrational numbers are the number which we can not write in the form p upon q, and here p and q are integers and q is not equal to 0. These numbers are like square root of 3, cube root of 3, cube root of 5. All these are irrational numbers because we want, for square root of 3 we won't get any exact value of this number. Similarly for this we won't get the exact value of the cube of 3. So that's why they are irrational number. And we have also discussed that a non-terminating non-recurring decimal is also an irrational number. For example, 0.42434459 and so on. This is an irrational number, and we have one more special rational number which is pi. And we know why pi is an irrational number, because we won't get its exact value. Pi is equal to 22 by 7, or this is equal to 3.1415925 and so on. So this is also a non-terminating non-recurring decimal. That's why this pi is also an irrational number. Let's represent irrational numbers on number line. First, we'll represent square root of 2 on number line. So for that we need to take some steps. So now let's represent square root of 2 on number line. For that I will mark 2 points O and A on number line, such that OA is equal to 1 unit. After that I will draw perpendicular on A, on perpendicular from A on number line, and this is my perpendicular. Okay, I will join these 2 points. This point I'll mark as C. Then with the help of my compass I will open OA, which is equal to 1 unit, and I'll mark on AC to get my point B, such that AB is equal to OA, which is equal to 1 unit. Now join O with B. See, this OAB is a right angle triangle that we know, such that OB square is equal to OA square plus AB square. We know OA is 1 unit and this AB also 1, equal to 2. So this OB is equal to square root of 2. So now this OB is equal to square root of 2. Now this OB, I will open this compass here and I will mark mark a point on number line, and this is I'll take as D, such that OD is equal to square root of 2, and this point D. The distance from O to D is equal to square root of 2. Similarly, we can represent square root of 3, square root of 5 on number line. Now, let's see how we can represent irrational numbers like square root of 3.5. Here we have decimal number inside. Let's draw square root of 3.5 on number line 5. For that, I will take a line which is equal to 3.5. 3.5, this AB. This point I will take as A and B. From B I will take one more point of 1 which is equal to 1 unit. So this C point. After that I will find the center of AC, and for that I will use this compass. For that we know we can do like this. So then join these 2 points. So I will get the center of this AC. So from here, now draw this semicircle with the help of this compass. Now draw perpendicular from B on the number on this line AC. This is my perpendicular. Now join these 2 points. I'll take this point as E and join such that this line touches this semicircle at point F. And this BF is equal to square root of 3.5. Now I will extend this line AC toward this. Okay, so and I'll mark these points here, 1 unit distance. So this is my number line now, such that this B is the center of this number line. So I'll take this as P. Okay, now I will open my compass. So PF, and I'll mark a point on this number line. So this point will be P prime. So this is my P to P prime. This distance is equal to 3.5 square root. So like this we have represented this square root of 3.5 on number line also. To prove that BF is equal to square root of 3.5, I have taken let x is equal to 3.5 here. Then we know OA is equal to OB, which is equal to the radius of this semicircle. Now we know this OC is equal to this full length AC divided by 2. This AC is equal to this full AC. The diameter of this semicircle AC is equal to AB plus BC. We know AB, this also equal to AB, is equal to x plus, and this BC is equal to, we have taken earlier, 1 unit, is equal to this divided by 2. So this is my OC. Now we can find this OB also, and this OB will equal to OC, this full, minus BC, and this OC we have find out this divided by 2 minus BC is equal to 1. So this will become equal to x minus 1 divided by 2. Now we know that this triangle OBF is a right angle triangle. So here we can apply Pythagoras theorem, which says that OF square is equal to OB square plus BF square. So from here we can find BF square, which will be equal to OF square minus OB square. We know this OF is equal to radius of this semicircle. So this will be also equal to, this also equal to OF. So this is equal to x plus 1 divided by 2 whole square minus this x minus 1 divided by 2 whole square. If you find out this, if you calculate this, you will get this equal to x. So BF will become equal to square root of x. Means here x I have taken 3.5. So my BF is equal to 3.5 square root. Hence we have proved this, and we can represent this square root of 3.5 on number line with this point P prime. We know that real numbers has a decimal expansion that we have learned, and we can represent all real numbers on number line. So here we have to represent numbers which are in decimal form on number line. So let's take one example here. Locate 2.665 on number line. So for that I will take one number line. So this is my number line. So I have to represent this number 2.665 on this. We know this number 2.665 will be between 2 and 3. Okay, now I will see this portion and I will magnify this portion. Then now I will divide this portion between 2 and 3 in 10 equal parts, such that these points are 2.1, this will be 2.2, this will be 2.3, this is 2.4, this is 2.5, this is 2.6, this will be 2.7, 2.8, 2.9 and 3. So see, my number is 2.665, correct? So this number must be between 2.6 and 2.7. Again I will magnify this number and I will see this number line like. After magnifying these 2.6 and 2.7, we have to divide this portion in 10 equal parts, like such that these parts are 2.61, 2.62, 2.63, 2.64, 2.65, 2.66, 2.67, 2.68 and 2.69, and my number is 6.665. So let's locate this number here. So this is will be, so see, this number will be between 2.66 and 2.67. Again we'll see this portion and we'll magnify this portion, then we'll get to represent this portion on number line and divide. Same, we have to divide this portion in 10 equal parts. Like now divide this portion between 2.66 and 2.7 and 2.67 into 10 equals part. Like these parts are 2.661, 2.662, 2.663, 2.664, 2.665, 2.666, 2.667, 2.668 and 2.669. So see, my number is 2.665. So this is my point where I can represent this number on number line. And this process is known as the process of successive magnification. And this with the help of process of successive magnification, we can represent all decimal numbers on number line. So you can represent this number also. Try to do this at home. 3.689, 4.235, all these numbers you can represent on number line. We know real numbers include rational numbers and irrational numbers, and in earlier classes we have discussed that rational numbers satisfy the commutative, associative and distributive laws for addition and multiplication. We have also discussed that if we add two rational numbers, or we subtract two rational numbers, or multiply or divide two rational numbers, we will get a rational number only. So it means they are closed under addition, multiplication, subtraction and division. Irrational numbers also satisfy the commutative, associative and distributive laws for addition and multiplication. But if we add, subtract, multiply or divide two irrationals, the result may be rational or irrational. Let's take one example over here. For example, I'll take this. For example, if I do for addition, I'll take two rational numbers. This square root of 2, let me take two irrational numbers, square root of 6 and square root of 6. If we add these two numbers, then we'll get, so let's see, for example, if I take two irrational numbers, square root of 6 and minus square root of 6, and if I add these two numbers, then I will get square root of 6 plus minus square root of 6, which will be equal to 0, and this is not an irrational number. Similarly, if I multiply these two numbers, then so I will get negative square root of 6 and square root of 6, which will be equal to 6. So this is also not an irrational number. Similarly, if I subtract these two irrational number, I will get equal to 0. And if I divide square root of 6 divided by square root of 6, negative, they will get cancelled. I will left with minus 1, and we know all these 0, minus 6, 0 and minus 1, they are not irrational numbers, they are rational numbers. So we can say that if we add, subtract, multiply or divide two irrational numbers, the result may be rational or irrational. Now, so let's see what happens when we add or multiply a rational number with an irrational number. Let's take is equal to 2, and I'll take irrational number as square root of 3. Now let's add these two numbers. After adding these two numbers, we'll get 2 plus square root of 3. We know this is an irrational number. It means this whole thing will be an irrational number. So it means after adding one rational number and one irrational number, we will always get an irrational number. So now see, if we multiply these two numbers, multiply is equal to 2 multiplied by square root of 3, which is equal to 2 square root of 3. So this is also an irrational number. So if we multiply one rational number with an irrational number, we will get an irrational number. Let's see for subtraction also. If I subtract 2 from square root of, if I subtract square root of 3 from 2, I will get 2 minus square root of 3. Or else I can do like this also. If I subtract rational number from irrational number, means square root of 3 minus 2. Both are irrational numbers. Similarly, if I divide, suppose rational number with irrational number, 2 divided by square root of 3, this is also an irrational number. Or if I divide square root of 3 and 2, I will get an irrational number. Here that the sum or difference of a rational number and irrational number is irrational, and the product or division of a non-zero rational number with an irrational number is also irrational. Now let's discuss about some identities of irrational numbers. For that, let's take A and B, two positive real numbers. Then these identities are, the first identity we have, square root of A multiplied by B is always equal to square root of A into square root of b, means we can separate them. And second, we have the square root of a divided by b is equal to first identity over here is square root of a into b is equal to square root of a into square root of b, means we can separate them. Similarly, second, we have the square root of a divided by b is equal to square root of a divided by square root of b. Here also we have separate these a and b, the square roots of a and b. So next, third identity, I have square root of a plus square root of b multiply by square root of a minus square root of b is equal to a minus b. Here we know this identity, x plus y multiply by x minus y. I have used this identity. So fourth, we have a plus square root of b into a minus square root of b, which is equal to a square minus b minus b. Here also I have used this identity. We know all these algebraic identities. We know this is equal to x square minus y square. So the fifth identity, I have square root of a into square root of b multiply by square root of c plus square root of d. So here what we have did, we have multiply a with c and square root of a with square root of c, and next we have multiplied square root of a and square root of d, and then we have multiplied square root of b with square root of c, and last we have multiplied square root of b and square root of d. So last identity here we have sixth one, square root of a plus square root of b whole square is equal to a plus 2 square root of ab plus b. Here I have used this identity, x plus y whole square is equal to x square plus 2xy plus y square. So let's do some examples related to these identities. So first question here is 5 plus square root of 7 into 2 plus square root of 5. So here I will use this identity, means I will multiply separately all the numbers. 5 with 2 I will get 10, and then 5 with square root of 5 into square root of 5 plus next I will multiply square root of 7 with 2, I will get 2 square root of this plus this will become equal to square root of 7 multiplied by square root of 5. Here again we can use this identity, 7 into 5, correct? So this will become 35, square root of 35. So I will write here square root of 35. So this is my answer. So second question here I have square root of 11 plus square root of 7 into square root of 11 minus square root of 7. So here I will use this identity. This simply I can write 11 minus 7, which is equal to 4. So here which identity I am using, this x minus y and x plus y, which is equal to x minus y, and here x and y are under square root. So third question here I have this plus square root of 7 whole square, which is equal to 3 plus 2 into square root of 3 into 7 plus 7. So this will become 10 plus 2 square root of 21. Here I am using this identity, square root of x plus square root of y whole square is equal to x plus 2 into xy plus y. Now let's discuss about rationalization of irrational numbers. We know when we multiply or divide two irrational numbers, the result may be rational or irrational. But when two irrational numbers are multiplied together such that their product is a rational number, then these two irrational numbers are called as rationalizing factors of each other. For example, if I multiply 5 square root of 2 with square root of 2. My answer will be 5 into 2, which is equal to 10, and this 10 is a rational number. Then 5 square root of 2 and square root of 2 are known as rationalizing factors of each other. Sometime we need to find the least rationalizing factor of given irrational number. For example, find the least rationalizing factor of 27 square root. We know we can write this 27 as 3 into 3 into 3, which is equal to 3 square root of 3. And if I multiply this number 3 square root of 3 with square root of 3, then I will get a rational number which is equal to 9. This is a rational number. So we can say the least rationalizing factor for square root of 23 is square root of 3. Now let's see how to rationalize a number like 1 square root of 2. Here the square root of 2 is an irrational number that we know. So how to rationalize these type of number? So what we have to do, we need to multiply both the numerator and denominator with square root of 2. Then we'll get square root of 2, and this will become square root of 2 into 2, which is equal to square root of 2 divided by 2. So let's take one more example. Let me take this number 1 divided by 2 plus square root of 3. To rationalize this number, what we have to do, we have to multiply 2. Here we need to change this sign. Here this is plus sign, we'll add here minus, and square root of 3, 2 minus square root of 3. So this will become 2 minus square root of 3 divided by 2 plus square root of 3 into 2 minus square root of 3. So this will become 2 minus square root of 3 divided by 4 minus 3. So which identity I am using? Guess. So this will become 2 minus square root of 3 divided by 1. So my answer here is 2 minus square root of 3. So here see, question arises why we need to rationalize numbers like 1 square divided by square root of 2, 1 divided by 2 plus square root of 3. We know that we can represent all rational and irrational numbers on number line. But the numbers like 1 divided by square root of 2, it is not easy to locate these numbers on number line. But if we rationalize this number, then we can represent them or we can locate them on number line very easily. For example, after rationalizing this 1 divided by 2, I got square root of 2 divided by 2. So now I can easily locate this number on number line. So this will be somewhere between 0 and square root of 2. Similarly, this number 1 divided by 2 plus square root of 3, which is equal to, after rationalizing we got 2 minus square root of 3. We can represent this number on number line very easily. So last topic over here, we have laws of exponents for real numbers. We have read about the laws of exponents in our previous classes. So same laws will applicable for real numbers also. These are a raised to power m into a raised to power n. If bases are same, then it will become a raised to power m plus n. Second, we have a raised to power m into n is equal to a raised to power m n. And third, we have a raised to power m divided by a raised to power n, which is equal to a raised to power m minus n. And fourth, we have a raised to power m and b raised to power m, which will become equal to ab raised to power m. Let's do few questions related to these laws. So first question here is 2 raised to power 2 by 3 into 2 raised to power 1 by 3, which is will be equal to, I will apply this law first. So this will become 2 raised to power 2 by 3 plus 1 by 3, which is equal to 2 raised to power 3 and 2 plus 1, which will be equal to 2 raised to power 3 divided by 3. They will get cancelled, so I will left with 2 raised to power 1, which is equal to 2, and this 2 is my answer. And second question here I have 3 raised to power 1 by 5 brackets 4. So I can write this as 3 raised to power 4 by 5, and this is my answer. Let's discuss about surds or radicals. We know the numbers like square root of 2, square root of 3, all these are irrational numbers. But what about numbers like 5? Here we have 4. What we call these numbers? And or 6, 11, all these type of number. These type of numbers are known as surds. And we can write these number as we know. We can write this 2 as 2 raised to power 1 by 2 and 3 as 1 by 3. And this number we can write 5 raised to power 1 divided by 4. And this we can write 6 raised to power 1 by 11. This square root of 2, square root of 3, all these are also surds. And these are also surd. We call them radicals also. And these surds or radicals are also irrational numbers. Always remember, every surd is an irrational number, but every irrational number is not a surd. For example, pi. Pi is an irrational number, but it is not a surd. And we have a rational number a, and n is a positive number greater than 1. Then square a, and here I write n, and or else I can write this as a raised to power 1 divided by n. This is called a surd of order n. So this number 5, and here if I put 4, then this is called, we can write this as, this is a surd of order 4. Like this we read these numbers. We have done all the concepts of number system. So next coming videos we will do all the exercises of NCERT book. Thank you everyone for watching my video.